本日の基調講演の講師、リンダ・リーカス様は、220以上の都市で女性にプログラミングを教える世界的な運動に取り組むレイルズガールズの創設者でいらっしゃいます。近年では子ども向けのプログラミング絵本「ハロールビー」を執筆されており、2013年度ルビーのプログラミングコミュニティにおいて最も有名な賞ルビーヘローに選ばれ、デジタルチャンピオン・オブ・フィンランドとして選出。2014年度にはステートアワード・フォー・チルドレンズ・カルチャーを獲得されるなどご活躍です。本日はプリンシプルス・オブ・プレイと題してご講演をいただきます。それではリンダ・リューカス様、よろしくお願いいたします。
Wonderful. My name is Linda. Yoroshiku onegai shimasu. I'm a children's book author, illustrator, a very mediocre programmer, and a business school dropout. So I never graduated from university. As you can see, my identity is a little bit all over the place, and this is a talk about those things. My childhood technology, the most creative and happy technology, comes from Japan. I grew up with Pokemon, Nintendo, and Tamagotchi, and I'm so honored and happy to be here today with you all. I've learned so much during the past few days. Just 2 minutes ago, I had this wonderful discussion with one of the translators that feels like my head is now spinning in a new direction, and I'm just really, really happy to be here with all of you. I'm the co-founder of RailsGirls, an international movement to give young women their first experience in software craftsmanship. This was started in 2009 when me and my friend Karri Saarinen wanted to teach ourselves programming, and we had never any idea that this would become such a global phenomenon. It was in Helsinki, Finland, where I'm originally from, and there was 25 of us, 25 of our friends, and we just wanted to do something that was colorful and happy and fun and reflected the Ruby community that I had learned to know. But then the internet happened. People started to tweet about RailsGirls, and you all recognize DHH over there, David Heinemeier Hansen, the founder of Rails, who said that something really cool is happening in Helsinki. And I remember being really excited. I printed out that tweet and put it on the wall, and I was like, wow, this is the best day of my life. DHH knows what I'm doing. And because of the internet, because of the global community that the Ruby community is, RailsGirls started to spread. And today, RailsGirls has been in over 260 cities all over the world, everywhere from Amman to Australia, from Belo Horizonte to Berlin. And it's all because of you guys. It's all because of the grassroots coaches, the grassroots organizers who fight every day to make this community a more colorful, diverse, happy place to be a developer in. I've been especially happy to see the RailsGirls community prosper here in Japan, where Ruby's dad comes from, and it's been a pleasure to see it grow. After I started RailsGirls, I went to New York to work for a few years for a company called Codecademy. Codecademy teaches you the basics of coding. It was a startup. It was run by 2 21-year-old boys, and the growth was explosive. We went from 5 employees to 34 employees. We went from 1 million users to 24 million users. And every single thing you can imagine that breaks in a person, in a company, or in a product broke. And I started to question a lot of the startup values and the startup world. The idea that the most scalable change happens when we make applications. I think the most scalable change in the world happens when you're a kid. If we can teach children to see the world differently, we'll have different kinds of adults. The most scalable change happens when you're 6 years old. And that's when I decided that I want to be a children's book author. In order to understand this whole story, we need to start from the beginning. And I think the beginning is that code is the next universal language. Every generation has some sort of a language that they speak, and at least in Finland, I think the 1970s had punk music that drove the whole generation. That was the anthem for them. The 80s had money. They were very money-centric in the 80s. And now for my generation, software and code is the interface to our imagination and to our world. And that's why we need a radically different set of people, a radically more diverse set of people building that world. We need more people not to see computers as boring or mechanical or magic, but rather as something exciting and fun and something that they can tinker and toy around with. My personal journey to the world of technology started when I was 14 years old. I had this big, huge crush on an older man. Everyone else at the time, they loved Lord of the Rings, Elijah Wood, Orlando Bloom, all of these actors and musicians. But I loved Mr. Al Gore. And Al Gore was the Vice President of the United States at the time. He was 50 or 60 years old, very weird choice for a young girl to be in love with. He wasn't the Oscar winner, he wasn't the Nobel laureate at the time, he was only the United States Vice President. But I had this huge teenage crush on him, and because at the time there was no Pinterest, there was no Facebook, there was no Tumblr, I did what every single teenage girl wanted to do. I wanted to express myself somehow, so I made him a website. And here it is. This was 2001, and I needed to learn PHP, I needed to learn HTML, CSS, how to set up my servers. And when this site was done, I felt so excited. This is what I want to do. This is how I want to change the world. And as a result, coding for me was always a tool of self-expression. A tool of self-expression, much like Legos, crayons, coloring blocks, guitar lessons, or theater had been years earlier. But then there were other boys. There were other things to get excited about, like social sciences and music and conjugating French irregular verbs and knitting socks and Bertrand Russell and his formal logic and philosophy. And I started to be one of those people who felt that computers are boring, mechanical, and somewhat magic. Here's what I think today. I think little girls don't know that they are not supposed to like computers. Little girls are very precise. They can concentrate well. They are really good at asking questions like what and how and what if. And they don't know that they are not supposed to like computers. It's us adults that do. Most of the adults think that computer science is this esoteric scientific discipline full of mystery, almost as removed from everyday life as nuclear physics. And to some extent, they are right. There is an awful lot of syntax, control flow, algorithms, data structures, paradigms, protocols, and practices, even before you can write the first line of code. Computer scientists are my biggest idols, but they've built so many layers of abstractions between the man and the machine that most of us have no idea how the computer works anymore. As a result, we teach kids in school how the human body works. We teach kids in school how a combustion engine functions. We teach even how they can become astronauts if they really, really want to become astronauts. But when your kid comes to you and asks, hey, how does YouTube know what to show when I press the play button? Or what is a bubble sort algorithm? Or Linda, is internet a place? We adults, we grow oddly silent. We say, oh, it's magic. Or we say, oh, it's really complicated. Well, it's neither. It's not magic, and it's not complicated. It all just happened really, really fast. The computer scientists of the world built these beautiful machines, but they also made them very foreign to us. And the language we speak to the computers, programming languages, are also foreign to us. As a result, no one noticed that a little girl, who I was, when I was conjugating French irregular verbs, I was actually practicing my pattern recognition skills. When I was knitting socks, I was actually following a sequence of symbolic commands with loops inside of them, because you know how in knitting you need to follow the instructions until you hit the elbow, for instance. Or that my love for Bernard Russell and his philosophy, and Bernard Russell's eternal quest to find the exact language between English and mathematics, actually found its home inside of a computer. I was a programmer, but I just had no idea that I was good at it. Here's what I think. If JavaScript is the new lingua franca, we need more poetry lessons instead of grammar classes. What I mean with that is that in the same way as you learn Japanese in school, you learn it by using the language, not only practicing the grammar. We need different ways of teaching programming. And in the same way as you learn Japanese by reading contemporary books, by reading classics, by writing news pieces and opinion pieces and poetry, we need different ways of using code. And at this point I decided that I am going to be that person who writes a book about the wonderful world of computers and technology and software and storytelling. There were only a few problems. First, I wasn't an author. I had never written a book before. Second, I wasn't very good at drawing at this point. And third, and the most important thing, I still considered myself to be a very mediocre programmer. I didn't have a PhD in programming, and I had no experience in early childhood education. But programming has taught me a lot of resilience and a lot of overcoming my mistakes. And I figured that, for instance, drawing, it's about mechanical repetition. That if I draw 1,000 circles, eventually the circles will get better. And here's a few pictures from that journey. These are the first pictures that I could find of Ruby. They are from 5 years ago, and you can see they are not very good. But I kept drawing, and I got a lot of support from the Rails Girls community. People all over the world started to send me pictures of a world of software where little girls would rule. And I got pictures from Taiwan and from Ukraine and from France. And slowly I started to feel that, like maybe because this Ruby community is so supportive, maybe I actually can become a children's book author. And I even got a plush toy from Belo Horizonte, and I felt that maybe there is something in this. And slowly the picture started to be better, and the story started to form around a little girl called Ruby and her friends. And I did probably the best or the worst thing in my life. I put this project on Kickstarter. Kickstarter is this crowdfunding platform where you can propose an idea and ask for people to pledge to help you in it. And I put Hello Ruby on Kickstarter, and in 1 month, it gathered over $380,000 worth of pre-orders. Everywhere from the world, from Amman to Australia, from Belo Horizonte to Berlin. The secret here is that I was panicking. I cried. I had no idea what I was doing at this point. And for much of the past 1.5 years, I felt like Alice in Wonderland, who took the red pill, who fell inside of the computer, and who's trying to find her way out. This was the photo that was on the Kickstarter page about the book. The idea was to do a storybook and a workbook that teaches you the conceptual ideas behind computer science. And as you can see, it's not very good. It's very sketchy, and it has things like bug Sudoku and my first error message, but it's not very structured and it's not very good. But what I've learned in the past 1.5 years is that unless you have the courage to put out the horrible first version, you're never going to get to the point where you actually have a book, a finished book, with many different pages, with a tested curriculum, unless you have the courage to do that first ugly draft. And much of the past 1.5 years, this was the quote that kept me going. It's from Ira Glass. He's an American podcast producer, and he says that nobody tells this to people who are beginners. I wish someone told me. All of us who do creative work, we get into it because we have good taste. But there is this gap. For the first couple of years you make stuff, it's just not that good. It's trying to be good. It has potential, but it's not that good. And the gap we all need to overcome is the gap of putting out the first horrible version even though it feels bad, because that's the only way to get better. So now the book is ready, finally. It was a year late on Kickstarter, and I felt horrible for all of the people who had trusted me, but now it's there. And the rest of the talk is about how I became a children's book author and the principles that helped me make this book and the future books that are happening. So I came up with 3 principles to help me make this book, the principles of playfulness, curiosity, and rules. And I did a lot of play testing in order to make the book right. And I also did a lot of play testing in Japan, which was super much fun. I can do 3 words of Japanese. I can do sugoi, kawaii, and subarashi. And that's all you need in playtesting. All of the exercises I'm about to show you are also available online for free, so you don't need to buy the book for it. You can print the instructions, you can see how they are done, and then you can also see what other kids around the world have done. This is a Danish little girl, and she password protected her door with a computer. So when you become a children's book author overnight, you need to pretty fast figure out what was the thing that I wanted to teach people. What are the basic principles of computing and coding that everyone should know? And I started with the story. I've already told you a little bit about Ruby. She's this completely fearless, imaginative, a little bit bossy 6-year-old. When her father tells her, Ruby, we're running late from school. You need to dress up really quickly. Ruby does dress up, but she leaves her pajamas on because Dad didn't specifically tell her to take the pajamas off. And when Ruby has a messy room, her dad comes to her and says, Ruby, you need to clean up your toys. They are all over the room. Ruby does clean up her toys, but she leaves her pens and papers on the floor because pens and papers are not really toys, Dad. And there's a chance that I'm teaching the most obnoxious generation of kids out there. But they also learn something very profound about how to talk to a computer. Mainly that you need to be very exact in giving the commands. You need to give the commands in the right order, and that you need to be very careful when naming things. The most important thing Ruby learns is that all big problems in this world are just tiny problems stuck together. All big problems are tiny problems stuck together. That's a really big lesson actually to learn. And that the curriculum of code is comprised of tiny bits that each and every one of us can learn. They are not magic and they are not complicated. For instance, algorithm. For normal people, it's such a hard and big word. Algorithm is just a step-by-step instruction to solving a problem. So for instance, you can explain an algorithm by talking about a cupcake recipe. If you have a good recipe, you can make blueberry cupcakes, but you can also make banana cupcakes. And you can make different amounts of cupcakes. And the concept of a loop, I'm sorry, there's the wrong English word here. The concept of a loop, the idea that a computer is really good at repeating something if you give the instructions. It doesn't need coffee breaks and it doesn't make mistakes. Ruby learns the concept of a loop by having a dance party. Ruby's favorite dance move goes like this. It's clap, clap, stomp, stomp, clap, clap, jump. And Ruby learns a for loop by repeating that dance sequence 5 times. She learns a while loop by repeating that sequence while I'm standing on one leg. And she learns an until loop by repeating that sequence until mom gets really, really frustrated. Ruby learns about decomposing a problem, about taking a big problem and putting it into smaller pieces by solving flowcharts. Here's a few of Ruby's friends, and you can see something went wrong with them. It seems like Android forgot to do something when his bath tube is overflowing. Seems like the fox did something in the wrong order, and seems like there is something wrong with Ruby's commands because she eats even though she's not hungry, and she's hungry even though she's eating. As you can see, these are not very hard and complicated things. You can teach them with very simple principles and very simple stories. And that's why I was so happy to hear yesterday that in Matsue you're also planning to implement coding into the curriculum in schools. In Finland, we're putting coding into the core curriculum in 2016. It means that every single 7-year-old Finnish kid will learn the principles of coding and computing in school. And they learn it through playing, through having fun, and not having one class for coding. So now I know what I wanted to teach, the curriculum of code. And then I needed to figure out how I want to teach these things. And I think there's 2 types of joy in programming. First of all, there's the more intellectual, abstract joy of writing a beautiful algorithm, or making a program that calculates the square roots of the first 20 prime numbers. And that's great, and that's amazing. But then there's the other type of joy in programming, the more tangible, the more physical joy of copy-pasting stuff together and hacking around and figuring, oh wow, oh boy, is this gonna work? Wow, I made this work, the computer obeyed my will. And I think that's called play, and play was what I was after. So I went to the people who know play best in the world, namely Sesame Street, that has been doing, I think, 34 years of television content for kids. And they say that play is paramount to our cognitive, our emotional, and our physical well-being. And I spoke with the people from Lego, who make the Lego blocks, and they defined play from 5 different angles. They say that play, there's physical play, there's play with objects, there's symbolic play, there's pretense and sociodramatic play, and there's games with rules. But for some reason, when we programmers, we think about play, we only think about games with rules. And furthermore, there are these different motivations for play. There's achievement-based motivation, there's social motivation, and there's immersion motivation. But again, for some reason, when we talk about gamifying education or playful education, we only use this one part of play. We use stuff like progress and power and accumulation. We talk about challenging others and numbers and optimization. And in reality, everyone here who's ever programmed knows that there's so much more. There's giving and receiving support. There's exploration and the joy of finding hidden things. And at least for me, there's a lot of escape from real-world problems. So at this point in my career as a children's book writer, I knew what I wanted to teach, I knew how I wanted to teach, and I was left with the question, why? Why I wanted to teach these things. And this is where the principles came in handy. So the principles of playfulness, curiosity, and rules. The first principle of playfulness is about asking the question, what if? And making the ordinary into something extraordinary. With the kids, I start by showing them these 4 pictures. I show them a picture of a computer, a dog, a grocery, of a car, a grocery store, a dog, and a toilet. And I ask the kids, who are usually under 9 years old, which one of these do you think is a computer? And the kids, they are very conservative. They say, none of those is a computer. I know what a computer is. A computer is the glowing box in front of which mom or dad spends way too much time. But then we talk. And we realize that actually a car is a computer because it has a navigation system. And a dog might not be a computer, but a dog might have a collar that has a computer in it. And there's robot computers, dogs, what are they? Computers. Grocery stores have all sorts of computers inside of them. They have cashier's machines. They have ice cream cooling machines. They have burglar systems. And then the favorite thing for all kids around the world is when I tell them that in Japan, toilets are computers and that there's even hackers who hack them. And that always cracks up the 6-year-olds everywhere around the world. The next exercise we do is I give them this sticker. And the sticker is an on-off button. And I tell the kids, this afternoon, you have this magic ability to make anything in this room into a computer by placing this sticker. And again, the kids are really confused. They are, oh, I don't know the right answer for this. I don't know how to make something into a computer. But then I tell them that your parents don't know either. They've just started to hear about this thing called the Internet of Things or IoT, and they don't have any clue either. But you guys are going to be the ones who grow up in a world where everything is a computer. Your toothbrush, your teddy bear, and your washing machine, they are all going to be computers. And you are the last generation that will remember the computer as a glowing box. And then this little girl comes to me and she's picked up this bicycle lamp. And she says, if this bicycle lamp were a computer, it would change colors, the light. And I say, that's a really amazing idea. What happens next? And she thinks, and she thinks, and then she says, if this bicycle lamp were a computer, we could go on a biking trip with my father, and then we could sleep in a tent, and this bicycle lamp could also be a movie projector. And that's the moment I'm looking for. Not the moment when they write the perfect JavaScript array, not the moment when they understand hashes in Ruby, the moment when they realize that the world is not ready. That technology is a really amazing way of making the world better, and that they themselves can be a part of that change. Chances are the little girl will never be the next Steve Wozniak, but for a moment there she felt as if she could create something totally new. I also asked the kids to imagine what is inside of a computer. Because again, we've made the computer so abstract that even as adults who are not computer scientists have a hard time understanding what happens inside of a computer. And I'll tell you, the kids are okay. The kids are really okay. They are amazing. This is what they come up with. There are the linkers, the kids who understand that computers are somehow interrelated, that there's components that link to one another, and usually there's some sort of a main component. They describe boxes and wire connections. There's the gear gurus. I love these kids. They imagine that inside of a computer there are some sort of gears, and it's really sort of steampunk, a weird way of seeing how old technology habits inside of a new technology. And then there are the drafters, the kids who really describe electronics and wires, resistors, all these things. And these kids understand that computers are not magic. They are made of hardware, they are made of real world things, and they are not magic. This brings us to the next principle, the principles of rules, of asking the question, how? How does this happen? The idea of imposing a logic on something otherwise very hard to understand. As you saw just before, the kids don't think that computers are magic. They at least have some sort of a hypothesis of what happens inside of a computer. They understand that technology is supposed to be taken apart. You're supposed to peek inside of a computer and see how it works. Unfortunately, the big companies of today, they are making technology more integrated and more hard to look inside. And they are kind of declining this experience from our kids. I think we need to explain kids what computers are in a totally new way. An average British home has over 200 computers inside of it, because a microwave machine is a computer, the remote control is a computer, the doorbell is a computer, but we don't see it like that. And the mental models we're offered for computing are really complex. I really like Alan Turing, I really love John von Neumann, but the language in which they speak is so abstract that it scares people away. Normal people don't understand what is a control unit or ALU or a CPU or immediate access store. So the way I teach kids what is the basic functionality of a computer is that you have data, something goes inside of the computer, so the input, something happens to the data, and something new comes out. That's what a computer is. Input, program, output. And the way we do this with toddlers is by building a cardboard computer, and the kid crawls inside of the computer. There's little instructions like, come out hopping on 1 feet backwards, and then they come out hopping on 1 feet backwards, and then the other kids need to decode what this input-output process was about. And that's how they learn what a computer is: input, process, output. Usually the computer breaks at some point because they start to run around like crazy. Final principle, principle of curiosity. The idea of asking the question, why something happens. Exploration, the joy of finding hidden things. We built our first computer with the kids out of paper. And you can find this online also if you want to do this evening with your kids. And we get to know the components that live inside of the computer. We get to know the bossy CPU, that bosses everyone else around but has trouble remembering things on its own. So it needs the help of the RAM and the ROM and the hard drive. And then we meet the GPU that is really good at drawing things, and so on and so on. And then the kids, after they've built their computers, they get to design their first applications. And one of my favorite stories is this little girl who wants to be a dolphin doctor when she grows up. A dolphin doctor. But she was really suspicious about this computer business because dolphin doctors don't really need computers, do they? But we spoke with her, and she ended up designing her own dolphin health application with a little dashboard for her dolphin patients and their health stats and so forth. And another favorite story of mine comes from this little boy. He's 6 years old, and his favorite thing in the world is to be an astronaut. And this is how the make-believe game goes. The boy is the mission control man. He has these huge headphones on, and he's completely immersed in his paper computer because he's built an intergalactic planetary navigation application. And his role is to bring the father on the opposite side of the room, the lone astronaut in the Martian orbit, safely back home to Earth. And I think these kids are going to have a profoundly different experience of what technology is, who can build with technology, and what kind of problems we solve. The ending. The roots of programming are in poetry and mathematics. The very first programmer in the world was Lady Ada Lovelace, the daughter of Lord Byron, the poet, and the mathematician Mum. And Lord Byron had all these wonderful, weird adventures with other women, and Ada's mum was really angry, and she was, "My daughter will never become a poet." But she was wrong. Ada did become a poet. Because Ada was the first one to see that computers were not only calculators, that computers were not only meant to calculate numbers. She saw that numbers can represent logic, and with logic you can represent anything. And that's what we forget, that the roots of computing are in poetry and math. The big idea here is that every single problem is going to be a computer problem in the future. I think all of you have trouble explaining your work for your neighbors or your family. If you're a physicist, it's easy. You study the physical world. If you're a biologist, you study the biological world. But if you're a computer scientist, people usually think that you study the computer. No, you don't study the computer. You use the computer to solve problems in the real world. And more of those problems are becoming computer problems. Problems with energy, problems with education, problems with health. And that's why we need more people to become computer scientists. The history of computing is full of exceptional, amazing, multidisciplinary people. People who are not only technical, people who have combined a lot of things. Alan Turing, already in the 50s, he talked about artificial intelligence and the child machine and how you could bring up computers like little kids, teach them to learn instead of just hardwiring them with data. Seymour Papert and Cynthia Solomon did a lot of work on trying to create practical applications for kids to learn about computing. The paper 20 Things to Do with a Computer is absolutely amazing. You should read it. And finally, Alan Kay, my favorite researcher of all times, he wrote this article called Personal Computer for Children of All Ages in the 70s. And if you look closely, you'll find a picture of a hackable iPad already in the 70s. It's really freaky and amazing. The more approachable, the more diverse, and the more colorful we make the world of computing, the better world we will have. We need more different people to solve these problems. And the good news is, I think the kids already know this. When I ask kids, what is technology? We have these kits where the kids get to answer these questions. One 9-year-old little girl would answer this. What is technology? What is it used for? And who uses it? Technology is electricity that loves. That's her definition. Technology is electricity that loves. And I heard that you have this concept of chi, of love, that is surrounding people and everything. But in the Western world, we don't have that. And the idea that technology is electricity that love is just very profoundly beautiful. And the kids know this already, that technology is something that is profoundly human. The DNA of the Ruby community is not the computers talking to one another, or the programs, or the ones or the zeros, or the machines. It's all of you, all of the people who talk to one another. The very word computer used to be a person who's really good at calculating things. And technology doesn't only mean, the very word technology comes from Greek, and it doesn't mean only the tools you use, it also means the skills and competencies and attitudes people have. I come from a country where this is very well understood. Finland, despite being the nation of Moomins, also has a lot of open source communities. We are the country of MySQL, Montevidenius and Morten Mikkos. We are the country of Linus Torvalds, Linux and Git. We understand that in order to make a change in the world, you need to give technology to everyone. So imagine with me for a while a world where the stories we tell about how things get made don't only include the 20-something-year-old Silicon Valley boys, but also the Norwegian librarians and the Kenyan schoolgirls. Imagine a world where the tiny Ada Lovelaces of the future live in this world of permanent ones and zeros, but are not afraid of technology, can see the opportunities it offers. Imagine a world of technology that is wonderful, whimsical, and a tiny bit weird. And now I'm going to try something that I'm not sure if it's going to work. Watashi tachi ga imamatte iru kangaekata ni eki o ataeta kodomo no koro no omoite o minna ga motte imasu. Kore wa watashi na story desu. We all have childhood stories that shape the way we grow up. The things we learn as little kids stay with us and influence the way we see the world for years to come. And that is why it's so important that you, as programmers, talk about your profession for your kids in the future. Thank you.
ありがとうございました。それではここで質問を、お受けしたいと思います。ご質問のある方、挙手をお願いいたします。
I need to speak a little bit faster now because I need to brief so much on stage. So, any questions? Well, I'll be here for the rest of the day, so if you have any questions, please come to me and ask anytime.
はい、いかがでしょうか。いらっしゃいましたら手を挙げていただけますか。どうでしょうか。それとも直接リンダさんとお話ししたいという方がもしかしたら多いのかもしれませんね。それではまた後ほど直接お話をしていただければと思います。それにしても恋が最初の原動力だったんですね。はい、これからも柔軟な発想、そして愛情、またその素敵な笑顔で、恋のようなワクワク感を多くの人に、広げていただきたいと思います。今日は本当にありがとうございました。
ありがとうございます。
リンダ・リューカス様でした。